I'm
just going to send you like encouragement. You're doing great, buddy. You're doing great.
Oh, yeah.
I believe in you.
Oh, yes.
Hey, Ken, you guys got you.
Before we get started, you know the orange forms? I was expecting each of you to have like 4, so you can fill out one section. That's 3 you can do for a student per sheet. So please fill them out as you go along, okay? And you hold on to them, you can give it to me at the end of the day.
If I got 4, I got
4.
I'm ready if you go.
Okay, so we say we follow the same pattern like in morning. And we don't need a time queue or anything.
I have my laptop.
Okay, cool. So we're gonna do 15, 17 minutes, and then Q&A and transition to the next, okay? Thanks.
So my name is Cameron Evangelista. I am an applied math and statistics major at North Carolina State University. And today I'm going to be presenting my proposal for the comparison and utilization of backpropagation and long short-term memory neural network methods to predict anaerobic bioreactor performance. So that's a mouthful, but we'll get into what that really means. So let's just dive on in. So when we're measuring water quality is measured with several different factors, a lot of which do not have very simple linear relationships. And so these relationships can be difficult to predict or model. So a lot of these models will be very, very complex. And so we may not be able to use simple models like regression models. And so the next best option would be a neural network. And the reason why a neural network is very desirable is that it can adapt itself and it can model and shape itself in order to form fit this model. And over several iterations, it will be able to tweak and shape itself to model the data very well. But we do not want to model the data explicitly well for fear of overfitting, so we have to choose the right amount of iterations for this neural network. So my research problem statement is to create 2 separate neural network models, one for backpropagation and one for long short-term memory. And then we are going to evaluate both of those and determine which one is better fit for a problem like this. So let's start off with backpropagation. So what is backpropagation? It's a process of sort of cycling through and evaluating the total error of your model, and then you're going to recycle through and tweak your model over and over. It's sort of a trial and error type process in order to optimize your model by minimizing the total error. And you use this using nodes, edges, and sample weights. And then the second network is called long short-term memory, which is a model that has the ability to predict and identify what it believes will be important towards the model, and it can choose to exclude certain pieces of information and include certain pieces of information that it deems unimportant or very important towards the progress of the model. So the goal behind this research, the overall encompassing feature, is to determine the power of neural networks and their effects on predictive modeling. And this could lead to major advancements in the field of artificial intelligence. Neural networks they're on the uprise in artificial intelligence, and they can help make machines and models able to, they can lead to advancements for machines and models in the fields of image recognition or sound recognition. Okay, so what is backpropagation? This picture is just very confusing, but I can break it down pretty well. So there is 3 layers. There's the output layer, the hidden layer, and the input layer. Now the input layer is what you bring into the model. The hidden layer is all the nitty-gritty stuff in the middle, and then the output layer is what your model spits out. So the hidden layer is not always just one small layer. It's usually made up of several layers built on one another. And backpropagation algorithms are made of nodes and edges, and each edge contains a sample weight that determines how much the 2 nodes connect with one another. So backpropagation has a process that goes this way. You identify the hidden input and output layers. Then you assign sample weights to each edge based on the nodes, or between the nodes. And then 3 is calculate the network output with the given values for each node and edge. Then you compare the actual output to your desired output. And if it's very far off, you go back and you recycle through and you edit the sample weights. And then you recalculate how much each weight attributes to the total error and adjust the model accordingly. And then you perform this cycle over and over and over until your error is minimized and your actual value is close enough to your desired value. So here's an example. So what we have is a picture in the top left is made up of 3 layers. The layer on the left is the input layer, I1 and I2. Then the middle is the hidden layer, H1 and H2, and then the output layer, O1 and O2. And on the bottom are the biases, but they are not very significant or small. So as you can see, W1 through W8 are the sample weights, and W1 is the effect I1 has on H1, W2 is I1's effect on H2, and so on. So as you can see, the value for W1 at 0.15, since it's less than the value for W4 at 0.30, what this is sort of saying is a rough example showing that I2 has a greater effect on H2 than I1 has on H1. And although you can't really grasp what this means, there is a table down below. So the picture up here, what we're trying to do is get this value 0.05 and 0.10. We're trying to get both of those values to become 0.01 and 0.99. We want to sort of figure out how we can shape those values into getting those 2 separate outputs. And so we want to figure out, how much 0.10 is going to affect getting to the 0.01, and then how much 0.05 is going to affect getting to 0.99, and there's a bunch of connections in there. And so when we run one iteration of this, we can see that the output 0.1 or O1 is 0.75, and then O2 is 0.77. Very far off from what our expected values are. But when we go back through and we tweak it, and we edit the sample weights over and over, and we do this 10,000 times, you can see we get a lot closer down here for the 10,000 observations, or the 10,000 iterations, and this is our target. We want to get to 0.01, 0.99, and an error of 0. So after one iteration, we have pretty high error, but after 10,000 iterations, our error is basically 0. So it doesn't have to be exactly 0 because you can't necessarily run infinite iterations on this. And so we mean that 10,000 iterations is basically 0 error. And so we have long short-term memory next. And so what that is there are 3 gates. There's an input gate, a forget gate, and an output gate. And what this means is the input gate is used when there's no information, or like new information. We want to determine how important this information is towards the rest of the network. Then the forget gate is used when we have a piece of information that's necessary, but it sort of fades off in importance towards the end. And then the output gate is all information that's sort of vital towards the entire progress of the network. And so we have an example here. Is anybody here like a baseball fan, softball fan? All right. So say, for instance, you're watching a baseball game with a friend, and your friend doesn't seem to care about what's going on in the game, and they only want to know changes in the score. So they get distracted, and you have to figure out what's important to tell them or what's important to keep in mind for later use. So what would be a good example of the input gate, forget gate, and output gate here? So for the input gate, it would be if the batter were to say, hit a foul ball with 2 strikes. So if you have 2 strikes and hit a foul ball, you have the same count, same number of people on base, nothing is affected. So that piece of information would get suppressed in reaching the input gate because we've determined that it has no effect on the model. So the forget gate would be to say if that batter hits a double on the next pitch, then the previous count has no effect on the model. Nobody cares how many strikes, how many balls there were in that count. So we can completely forget the information we used to memorize that count. And then the output gate would be, say, a piece of information like that person who just hit the double, they're now on second base. And if you were to, like, the score is the same, but if you were to say hit a home run right now, that instead of being 1 run, it would now be 2 runs. So we want to keep that piece of information there, but we would suppress it from going to the output gate. The output gate would be if somebody were to hit a home run or somebody were to just score. But that piece of information you don't want to send to the forget gate because it's going to be useful later if, say, somebody hits home. Okay, so there are several key papers. The first of which came from China, and it was to use a long short-term memory-based model for predicting water table depth. And an interesting thing about this was for all these neural networks, the more data you use, the more accurate it's going to be. You want to train, test, and validate your models. And so what they used was 14 years of irrigation data. And the interesting thing about this paper was they implemented a dropout method, which is sort of a backpropagation type form. But what it means is, as you can see, every single node affects every other node in the hidden layers. But what this dropout method does is, in order to prevent overfitting, which means you make a model strictly designed to satisfy this data set, but once you bring in another data set, the model is so tailored to this one that it's kind of off the other data set. So the dropout method is where you randomly select certain nodes and you only use those. Throughout each iteration, you would recycle which nodes you randomly select for the other iterations in order to prevent overfitting. So it's like if you were to sample a population by choosing everybody in the population, not necessarily sample at that point. You want to break it down and you don't want to be as complex as you need. Okay, and then the second paper was about using a multi-layer perceptron neural network. And what this paper focused on was the versatility of neural networks as a whole. And so what the researchers did is they took 1,300 images and they tried to train a neural network based on age and gender. And what this neural network was able to do was take images submitted and determine the age within reason of each person and their gender based on identifying patterns found in both the teeth and the bones. And so you can see that neural networks are able to identify things that we can't. I've never been able to tell somebody's age based on their teeth, but apparently neural networks are able to do that. And then there is a last paper that is on the estimation of biogas and methane in a potato starch processing, in treating potato starch processing wastewater. So what this one did is it combined backpropagation artificial neural networks with, it compared them with nonlinear regression. And in the statistics world, everybody talks about regression. It's the greatest model ever. But when it comes to comparing artificial neural networks, the neural networks were able to show greater improvement with R-squared values above 0.98, whereas the multiple nonlinear regression were only able to reach R-squared values as high as 0.93. So the backpropagated models were actually deemed better than the nonlinear regression. So the way I plan to structure all my research is I have a data set of water quality data, and I'm going to send it to both a neural network, or a backpropagated network, and a long short-term memory network. And then I'm going to use the data set to train, test, and validate each network. I'm going to optimize both networks, and then I'm going to compare to the original data to determine how much fluctuation there is between the error and between the actual and the desired results. And then I'm going to bring it all back together and compare which model I believe works better for this sort of situation. Okay, so what would I be modeling? I would be modeling the actual recorded values, comparing those to the values calculated by the model. So I just want to verify the error, and as the model were to update itself, we would be getting new values for error over and over, and the model's going to shape, shift, and form in order to be able to optimize the error perfectly. And so this is going to be done over the course of many iterations. As you saw in the previous example, there were 10,000 iterations in this model. So they're not always going to be small. Some of these models are very computationally intense. And so this is going to be done many, many, many times and can be very, very complex. So what would be the constructs I'd be using? I would be using artificial neural networks because they can basically model a brain in certain areas where just a program wouldn't be able to sort of think for itself. These networks can quote unquote do that, but their ability to adapt and sort of form fit the problem would be ideal for modeling this sort of situation. So what kind of models would I be building here? The models I would be building, they'd be more empirical, but they would also be mostly computational, as the relationships between water quality can be modeled with several of these mathematical equations. The importance of which I haven't fully identified yet, but I'm sure they're going to be coming to equation later. And so I will be using software tools such as TensorFlow and Python to create these neural networks. TensorFlow is known for machine learning and deep learning. And TensorFlow is great for creating neural networks in this sort of situation. So the results that I hope to obtain are clear and concise for both models, and I hope to see both models accurately predicting the data. I hope to see little to no error between the measurements, and I really hope that it's sort of clear which model works better, but I would like for both models to be very accurate and predictive results. And then here are the references. And if you would like to learn more on backpropagation, Mike Mazur on top has a very, very descriptive article, and it lays it out step by step perfectly, and it was really, really easy.
Question?
Yes.
I was curious, are you planning to build your own LSTM or utilize one that's already there and modify it to what you're trying to achieve?
I don't know one that is already there. I'm probably going to start from scratch, I would believe, because I don't know too many. I don't know too many previous TensorFlow programs, and I believe my grad student's going to help me start from scratch. Yes.
Cameron, can you give examples of what, for the water quality, what inputs are versus what the outputs are?
I haven't gotten to see the data set yet, but I believe, I don't know how they score water quality itself. I just believe it might be on a categorical sort of scale, but I believe they just have several factors and just listing the quantity of the factors and how much influence they have. But I'm not sure how they calculate the overall water quality. I'm not sure about that yet.
Cameron, following up on the same question, not about the water quality, but the input. What are some of the possible properties that will be input to this model?
Like some of the factors are how close it is to agricultural areas for pesticide runoff, erosion in the area, how close it is to a city, if there's cattle nearby, if there's homes nearby. Those are the sort of factors I've been told are in the data set. Again, I haven't actually seen the data set to be able to verify, but it's most things like that, mostly the pesticides.
But is there, in addition, a time dimension? Meaning, is it like a progression of data, or is it like static one?
I think it is over time, and I think it's multiple locations over time. I believe that's what Dr. Dang told me, but I will have to verify.
So you said something about TensorFlow software.
Yes.
Have you addressed that issue yet? Or?
I'm working to figure out a way to download it. Dr. Dang said she has some way that she thinks she can help me get it onto my computer. But as soon as I figure out how to download the software, I'll start building networks.
Any other questions? Any of you have questions? Okay, Cameron, thank you.
I don't even know how my brain was to
Because you're just not turned off.
Right. So my name is Fagan. I go to Interstate. I'm a rising sophomore in mechanical engineering and mathematics. And my project is finite element modeling of flash thermographic detection of defects in a steel plate. I'm working with Dr. Sundaresan. So to start off, defects are inevitable in aircraft structures that are made of metal, composites, or hybrid. So a lot of the times they come in during the manufacturing process or just during the normal service life of a component. It's kind of hard to make perfect things every single time in the manufacturing process. And with things in like aircrafts, when you have giant metal wings or composite wings, one of those, when they're working on them, they're walking over them, they can drop hammers, they can just make indents with their feet, because with a lot of composite materials, which are materials made from two or more materials with significantly different physical or chemical properties, more simply obtained at the macro scale level by simple mixing techniques. So a lot of the times, they're really strong in one dimension, but not so much in the other one. So they work really well with aircraft in terms of like the wind and how it like distributes across it. But it's really easy to damage just by dropping a hammer or something like that. And so that's kind of what I'm working on. Yeah, and then hybrid materials, they have constituents combined at a nanometer or molecular level, which is a lot smaller level than normal composite materials like you see in aircraft most of the time. And yeah, so runway debris or burrs or foreign particles, any of those things can come in and start causing defects in planes. And like I said, tool drops or humans walking over parts is another thing. And so to identify defects like that, we use non-destructive evaluation technologies, and they include acoustic emission, ultrasonic testing, thermography, and more. So non-destructive testing, like Walker talked about, is a wide group of analysis techniques used in science and technology in the technology industry to evaluate the properties of a material, component, or system without causing damage. And then acoustic emission, ultrasonic testing. Acoustic emission, like Walker talked about, yields sensors reporting stress or sound waves from some external stimulus to a structure in order to try and locate defects in their magnitude. And ultrasonic testing uses sound energy propagating through the material being tested, which will be reflected when there's defects in the wave path. But I'm focusing on thermography. And in thermography, there's an inspector that uses an infrared camera in a passive mode to measure the steady state surface temperature of a component. It assesses large areas of structures in a relatively short duration of time, with heat applied to the surface of the test object by an external energy source like the IR camera. And then because of that heat pulse that's there for a second or two, or much less time, temperature rises instantly on the surface, and then the surface temperature is going to change because of that. And then as the heat moves through the surface, you're going to have a rate of change of the surface temperature as a function of time. So it's not just constant change, it depends on the time. And we can use it as a predictive or preventive maintenance technique. And predictive means that you're just going to determine when maintenance should be performed based off, like with cars, after every certain amount of miles, you want to get your tires changed, things like that. And preventive is just regular maintenance performed while the equipment is working to decrease the likelihood of a component failing. So just actively working on stuff, making sure it's all good. And with the future of that is going to be, currently we can't really do too much with aircraft while they're in the air, or going towards working on that. And an infrared camera, if you don't know, is a non-contact device that detects infrared energy or heat and converts it into an electronic signal, which is then processed to produce a thermal image on a video monitor to perform temperature calculations. So the thermography process can be simulated using finite element analysis tools such as Biogas, which is what I'm going to be using for the rest of this research. And finite element analysis is a numerical method for solving problems of engineering and mathematical physics, and it subdivides a large problem into smaller, simpler parts that are called finite elements. The simple equations that model these finite elements are then assembled into a larger system of equations that models the entire problem. Basically, it's really hard to take one giant surface that's not really uniform and use equations to model it. So if you do a bunch of little ones, you can put them all together into a system, and that models what you're working on. So yeah, Biogas is a finite element analysis software that can simulate incredibly complicated components, structures, and systems under a wide variety of situations and loading conditions. And in my case, loading conditions and other types of, not thermography, but other things that are stress tests, you can put weight, that's your loading condition. For me, the amount of heat / time we have it out, like the temperature it's at, all those are loading conditions. And so from one of the papers I'll talk about later. There's just a visualization of finite element representation. So CAD, or computer-aided design, you can work in a simple geometry and then make it into more complex. Like someone drew a missile over here, and you can use SolidWorks, AutoCAD, other things for that. And once you have that with finite element representation, you break it down into smaller and smaller pieces. And if you see, it just looks like a bunch of dots from back here. It's just thousands, or sometimes even much more than that, little elements inside of that. So my research problem, I'm going to examine the effects of defects in a thick steel plate. So even though I'm not working with composite, I am still working with steel. And we're going to look through the temperature variation observed in a 1/2 inch thick steel plate during the thermographic process. And we're going to perform a transient heat transfer analysis to simulate this temperature variation. The transient just means it's going to be a very short amount of time. We're going to add a heat pulse, which will be there for, I think, a millisecond or so. And we're going to measure how the temperature moves throughout the surface after that. In a steady state heat transfer, the temperature of any particular point in the system just remains constant after equilibrium is attained, which would mean just after the heat is added. But since we have the temperature changing, since we have a transient flash, and that's moving through the material, it's gonna keep moving over time, so we don't do a normal steady state one. And this is a picture of this is a cross section of the steel plate I'm gonna have. So if you imagine just a circular plate with a cylinder kind of just drilled out, going through, and instead of going all the way down, it goes just about down to here. So we have an axis symmetric model, so just symmetric about an axis. And so you can just visualize if you have the plate revolved around here, going like this, or looking from the side, going that way. And so H is going to be the 1/2 inch of the steel. L is going to be the radius of the steel plate right there, probably 1.5 inches because we're thinking about a 3-inch model, but that's subject to change. R is the radius of the defect, which we're going to have 4 to 5 different models, so it could vary from 1/8 to 1/4 of an inch in radius. And D is the difference between the height of the length of the defect and the length of the bottom. So probably about 0.4 inches because we're thinking of doing 1/10 of an inch depth of the defect. So research goals to create a model that shows temperature variation across the plate due to defects of different sizes. And we're going to use the finite element model to study the effect of defects in metallic plates in terms of temperature variations. And then one of my later resources, just a picture talking about finite element analysis. So finite element solution of a mathematical model, you choose your finite elements, mesh, which I don't have to worry about right now. You represent your boundary conditions, such as, in this case, how much heat, what's the length of the duration of the heat flash, things like that. What's the geometry of the situation? And then we solve, and then we assess the accuracy of the finite element solution of the mathematical model, and just go back and forth until we get up to where we want to go. So yeah, it includes the kind of loading, so heat, how much, that. So some of my key papers and just other references, the Abacus documentation, I'm using that for, Abacus is the only software I'll be using, I think, for all of my research. It talks about the scripts, because it has a Python script, it's also really easy to use throughout because it's like other CAD or SolidWorks applications where it's really like user-friendly, it's more visual than straight programming. And then the picture that I had before and the visualization of the missile, it's from an article called Why Study Finite Element Analysis. Then we have another couple ones. We have one called Thermography as a Tool for Damage Assessment. And so that study was just focusing on the use of finite element analysis to simulate the thermographic process for complex geometries and provide information about the process of using software for finite element analysis. So that's just, it was a little bit more complex than the geometry I'm working with, at least it seemed so when I read it. And there it's just kind of showing me, it's another, there's one of like many articles I've seen using thermography. I haven't seen anything exactly what I'm doing, but a lot of things to get me like started with that, seeing how it should look, things like that. Because it's kind of hard to visualize what the whole process is going to look like since I haven't actually learned dynamics or things like that, but I'm learning a lot by reading these. And then we have one called non-destructive testing and evaluation. It's just explain non-destructive testing, like I mentioned before, which is a branch of material science and engineering that is concerned with all the test methods used for ensuring uniformity, quality, conformance, safety, and reliability of materials and components without impairing the intended use. And we have just a couple more. Composite defects and their detection, just provide more information about the various defects, where they arise, and detection techniques, which is what I'm working on. And then one by Dr. Sundaresan. He has two papers. I'm focusing on this one, which is called Normalization Procedure for Pulse Thermographic Non-Destructive Evaluation, which describes thermographic non-destructive evaluation, provides information about pulse thermography, how it works. I'm kind of just working further along with what he's done before. And then one called A Review of the Thermographic Techniques for Damage Investigation in Composites, which provides more information about IR thermography. And so what I'm going to be doing is using Abacus, creating axisymmetric models. We're using the properties of steel because you have to put in a lot of data for it to work. It's not, as long as you have all the data, it'll be really easy to use. You just have to make sure you know all the properties about it. And we use it to create a 1/2-inch thick plate with 4 to 5 different defect combinations, differing in diameter with 0.1 inch of depth. I'm going to make 4 to 5 separate models and then just look at all of them by themselves. And I'm going to simulate a uniform heat flash for around 1 millisecond. And we're going to define elements within the plate in different locations. And then right after the heat enters the plate, we're going to measure the temperature of the elements and then as well as how it changes over time. So here's a picture. This isn't exactly what I'm doing, but it is a different example I found online of someone doing a transient heat transfer analysis example in Abacus. And just what I believe is the different colors correspond to the heat and how it's moving. I couldn't get an animated version, but it does. You can see with the video how it's moving from left to right and the colors are changing over time. So that's kind of what it'll look like with what I'm doing, just like a different shape. And it also wasn't broken down in as many elements, at least you couldn't see it in there, but there are going to be hundreds or thousands of little ones. And so I'm going to create a mathematical model and set of equations that represent the change in temperature across the elements within a cross-section of the steel plate. And what I expect is for the results to show that the temperature difference between a defective and non-defective area of a steel plate should be non-zero, and temperature changes accordingly for varying defect sizes, because the heat's not going to be able to travel the same way throughout normal air than if it's moving through the metal. And so when we're mapping out that, what I should see is kind of just curves and heat pulses moving over time. They should be kind of drastically different for an area that's not defective, for an area that is defective. And if it's a different size of a defect, it should change differently, things like that. And then eventually, further on down the road, these results could be used to predict the location of unknown defects. Right now, we're just working on if we have known defects, we know their geometry, their size, all of that. How is that going to affect it? And then later on, we can do that with further research to figure out how to find the defects when we don't know how big they are. And that is it. If anyone has any questions.
Could you go to that cross-section figure?
Yeah. So rough drawing.
Yeah, so tell us about this one more time.
So it'll be like a circular, imagine like a cylinder of steel, 1/2 inch thick, and then in the middle we have kind of a circular, like, so when this is revolved around this axis right here, this will form a circle, and it's about 0.1, this is about 0.1 inches in depth, and this will vary, the radius will vary. I think right now I'm not too sure, I haven't talked to Dr. Sundaresan because he hasn't been here recently, if they're all going to be centered or not, which it should be because it's axis symmetric, but it should just change in radius, and so we should have, I think, between a total diameter of between 0.25 and 1 inches.
So you keep saying plate, so where's the plate here?
The plate, that would just be the whole thing over here, and there's a hole in it.
The cross-section.
Right.
I'm missing it. So it's like a
This is
circular
really just
plate?
half of it. It's upstairs.
Yeah, it's like from, like, this is the center.
Right.
Yeah, so you have to kind of project it around.
Yeah,
It's like a circular plate.
yeah, circular plate.
And then,
And then from the top, we take out a little bit.
so the defects would be where? It could be anywhere.
This would be the defect. It's rather than have one solid
I see.
cylinder, we would have just like kind of a hole through it, so that when the heat's traveling, it's going to travel differently through this blank air than versus the rest of the metal. And we're going to look at that.
So So what's the interplay between the heat transfer and any kind of defect analysis? What are you trying to do here?
I think what we're trying to do is see basically how, by seeing how the heat transfers with a different defect, examine how it corresponds to all 5 different, or 4 or 5 different combinations, just to see how a size of it affects the change overall in the heat transfer. And then from that together with the model, I think later on down the road, you could use that to seeing how the temperature changes. If we have a different situation where we know the temperature or something like that, kind of predict where the defect should be based on its size that we've worked on. Kind of like going from defect to temperature variation and later on finding an unknown defect.
So in your case, the data set would be just that on one configuration, just that one plate?
Yeah, and I think we're doing just a couple of those and just working with Abacus with that. I haven't been able to use Abacus much yet. I've been watching a couple tutorials.
Any other questions, guys?
I have a question. You stated that you might be using Python. How would you?
I think it's the way it works is there's Python scripts for it. I've only opened it a couple times trying to understand how it works. I know it has a loading screen where you can use Python scripts to work with it, but I think most of what I'm doing, you can just use an interactive software within it. Yeah.
Take one more question. So are you going to do anything in the lab? You said the 1 second flash.
I think it's all supposed to be simulated. I don't think I'm actually, because I know Dr. Sunderson showed me a plate from before, but I think I'm simulating just separate ones completely in Abacus.
Very good, thanks.
Yeah. There we go.
4 minutes ahead of schedule, so we have some time. You can wait for 2 more minutes and we start.
Good afternoon. My name is Kennedy Garrett, and I'm a rising sophomore at State University, majoring in electrical engineering. And my mentor is Dr. Jane, and my title is Analyzing Decision Making using the Lens Model. So my outline, first we go to introduction, research problem statement, research goals, key paper, and methodology. So hunger is a big problem in the world, let alone the country. So 925 million people are hungry worldwide. And 46 million people are hungry in the United States alone, even though we're really developed and good at a whole bunch of other stuff. The simplest thing like hunger is a big problem. So in state alone, 15.1% of North Carolina are food insecure. According to USDA, a food insecure household experience frequent intervals of interrupted availability of nutritious food. So people, they may be eating fast food, like that's not good for you, like vegetables, stuff like that. People aren't in places, so because it's such a big thing and people recognize it, this is how food banks became established. So that's how the food bank of Central and Eastern, that's North Carolina, became established. And that's their logo, or it's in the middle of the screen, and the part that's green, that's the part that they serve. And they actually serve green. They serve 34 out of 100 counties of North Carolina, utilizing 6 locations. So food banks mostly run off of monetary donation, volunteering, food donation, and partnering agencies. So they get a lot of their food from places like Walmart, stuff like that. Like any type of grocery store that we shop at, they donate their food. And so food banks are responsible for making like really big decisions, like how much food goes here, what type of food goes here, and that. And so my research proposed that we could use a lens model that I will explain in the next slide to determine how to increase their supply of food and how to help them make better decisions to get more food. So the FEED project, which is the flexible, efficient, effective, equitable distribution, they are funded by the National Science Foundation, and that's like the umbrella. So I work under my project. And so one of their goals is to make smart systems. So it's like the app. It's like an app. They basically put in information, and they're going to tell us like what to do. So then we have the food banks, and the food banks will help combat food insecurity. So this is the lens model. So the criteria is that this is what actually happens in real life. And then the ones, Q's are the ones in the middle. That's like how we get our judgment, which is our guess. And then what connects the criteria and judgment is the accuracy. So this you better understand. So you can better understand. So let's say a high school senior was trying to figure out what college to go. Some things they might look at is like the cost of tuition. They might look at how much money that's bringing into the household. They might look at how far it is, how close it is to it, and like their majors, stuff like that. So the food bank, so my research problem statement is to end hunger so my hope, distribute food that are perishable. So things like fruits and vegetables, that's something that we really want to get out there. And that stuff can go bad, unlike cans. So you have to make a timely decision to minimize waste. Because with cans like that, you can make a decision like 3 months later down the line, and that's fine. But with fruits and vegetables, you have to make it fast. And to assist them, we want to necessarily capture and model their judgment policy, decide what cues they're using in their decisions. So our research goal is to build a computational model to capture decision-making, judgment policy, and to identify essential cues utilized by the decision makers. So here are some key papers that I use in my proposal and my project. So the methodology, so we'll be building, we'll use the food bank of Central and Eastern North Carolina as like to collect data. That's kind of like the first, that's where we're collecting our data and we're kind of basing them off of all food banks. And then eventually we want to use this hard technique to help other food banks across the country. And math constraints I will build the math constraints we will use are the coefficients of determination, and the computational model we'll be building is linear. The software tools we'll be using is our Excel and type of results that we seek to obtain the essential cues that the food bank of Central and Eastern North Carolina operational managers use to make decisions.
15 minutes. So, when you say you would model, I mean, you use the word cue and you use the word model. Can you explain what cues you're referring to?
Cues are like what we use to make decisions. Like if you want to decide where you would stop to get breakfast on your way to work, you would think about how far it is it on your way there, and how expensive it is. How expensive it is.
I mean, in reference to food bank.
The food makes, okay. So they have to make decisions on like how they get food, and they have to decide who gets how much food and things like that.
How is that determined?
Sorry,
How is that determined?
how to determine like how
How much food someone gets or a family gets versus another?
well, the food bank of Central and Eastern North Carolina, they have a thing where people can go and pick their own food. But I was saying the operational managers, they have to decide they have 6 locations. They have to decide how much food goes to each location.
So let's discuss this a little bit more. When you say cues, try to differentiate between what's input and what's output. So in the food bank case, where you send the food is more like an output, right?
Yes.
Like a decision.
Yes.
So what is the input? What are some of the input cues?
What do you mean?
I mean, like the decision maker, what are they using to make the decision? What are some of the factors which you call cues?
That's what we're figuring out during the research. Because the research, what we're going to do is going to be an experiment. We're going to have volunteers come in. We're going to give them a case study and ask them to make a decision, and then ask them what they do to help. What is they thinking to help make that decision?
So is this your methodology slide?
Yes.
So again, you cannot skip the idea that you're going to bring a case study. Can you tell us more about what that case study is?
We haven't decided what the case study will be.
There were 2 other subjects.
Probably these guys. Probably.
So anybody can be a subject of this decision.
Well, we haven't. The ages probably vary, but we haven't.
So, in your mind, what is the value of the lens model method? What is it trying to do?
We're trying to figure out the cues. That's what the whole research is about. We know what's happening in real life, and we know what they're gonna guess. But we're trying to see what the cues are.
Okay. There's kind of single level and double level lens. Have you looked at that any? Okay, so you're just doing right single. Okay.
Okay, can you guess what could be some of the factors, cues? Let's say you're the decision maker for food bank. You get a bunch of reports. What do you think may be the factors that you look at?
We probably look at how, for each location, how many people that they bring in, what they're most likely getting. Like, are they getting more produce than they're getting frozen food, things like that.
Kennedy, I think you skipped several key steps of the methodology. Now we have the scripts of the interviews. You're gonna try to understand, figure out, and you're gonna design the scenarios. You're gonna recruit participants. Although I thought there were some slides you talked about this empirical study, which is missing. So you did your IRB. Was that okay?
So would they be choosing food based on what they think people would like or what they think people would need? Like, do you think they would choose food based on like people here may not be eating very healthy, or do you think they would choose food based on like the region itself? You know, maybe?
What the food bank was set up?
Yes.
Well, they'll probably look at the data that they're, like how much people are getting, but then we want to promote nutritious food.
Okay.
So one thing, let me just ask this question. So whenever we do a proposal, I mean, regardless whether you're doing a thesis or anything, right? At the proposal stage, you should be very clear, at least somewhat clear, what happens after you start your research. Do you foresee what you're going to do here on out, beginning next week? What are the steps you're going to do to complete your research? Do you have a good idea?
We'll start to design the experiments.
Design the experiment?
Yeah.
Okay.
Wrap the case study. And like develop the case study and things like that.
Well, I'm pushing this only because we have more time. So what would the case study look like? Would it be a bunch of text? Would it be data? What would it look like?
It'd probably be a combination of both.
Any other questions? We have like 8 or 9 minutes. I think since the other people who said that they will come are following the schedule, I think we should just take a little break and start close to 2 o'clock. Because otherwise everybody else will be. So now.
Ready?
Yeah, I have. Sure.
Can I go ahead and start?
Yeah, you can start.
Thank you. Representing the room.
Yeah, I mean, I told them I'm on the others. They can find the others, but they just like,
He's talking about feedback.
Your stuff sounds super cool. Both of you guys' projects actually sound super interesting. Mine, like,
Basically saying.
like I'm okay with it. Both of you guys' stuff, like, I didn't know.
It was a miscommunication. Thursday night.
But I'm pretty sure. Oh, no, that's actually great. We're not
Yeah, they've already.
That's nice.
I see like cars, and I'm like, and got a little robot the size of a water bottle.
Y'all do the little robot though? I got you.
Yeah, you can drive a little robot around that line.
Yeah, like second 90%.
Can't do that, like a quarter of it.
Nice. Thank you. I appreciate it. Yeah.
How is that?
Your wife?
So I either say that he's like, oh, he gets it, or he's like, there is so much less patient.
That's why right before I presented it. Oh, I thought you were Western Europe, like somewhere in there. Like Ukraine?
No, but like she asked me. I really like. Okay, cool. That's a good question. Over here.
Oh, yeah.
I was 12.
So,
Yeah, as soon as you get to my presentation, you're like, yo, you gotta stop. You're gonna hold your
we
I don't know what you
might
mean.
be tons of points when I
Oh god, yeah.
Well, when you were looking at this, so you did that. It's so funny.
It was there for like a second. It was there for like a second.
It's over.
I didn't research. This isn't in PowerPoint.
What does it mean? What's the thing you made it?
It's a package for LaTeX. It's like a tic-tac typesetting. It's like a tic-tac.
Okay.
It's a.
So basically, an extra for no reason.
Maybe it's a lot better than PowerPoint.
Pretty much.
PowerPoint.
He already has a better title than ours.
They give me like 3 extra months.
Also, the next DHS.
What? Yeah. They use LaTex.
Oh, they got almost.
You were the first person I saw. I was like, hey, that's your advice.
I had to make this about you. Talking about me. Talking about you.
Yeah, I wanted
Thank you. Everyone tell me how good I look.
You did your makeup.
I know.
Go.
Thank you. See, someone knows how to get compliment.
You look nice. You look nice to talk. That's so messy.
I want a little robe, some leather jacket.
Someone else you can
Yeah, I want a little robe, leather jacket.
Just like that, like the ball.
Take a drink, you know?
Like the color red. Yeah. Baby doll.
Oh, baby doll.
Okay.
Okay. See the wrapper all there. Imagine like with
He was there for everything. He was there for everything.
Shorts and like a long sleeve button up.
No, I just didn't want to wear pants.
All right.
how long is that? How long is that?
Funny and probably wear it all the time. Like.
Validation. I can still get dressed when they get on.
Really?
So,
I went to Harris last night. I'll be gone.
I'm just like,
For like 3 days.
He was like, oh,
Yeah,
I'm
I'm
going
gonna
to
come back
dress.
on my bed.
I forgot that I had to. I was like, the restaurants. 2 in a row yesterday. While you're driving, it's probably.
Just so funny.
No, like, I was like,
Would you wear your pants up here?
They give you, I
no,
know,
like, I
don't
keep
have to drive around.
I'll just wear it.
I'm like, my neighbor, like, it'll be super over.
Are you talking about just that?
I'm gonna go through my entire wardrobe.
What's the bar?
Presentation. I couldn't understand the presentation for your entire college.
I didn't even know this.
And there was no button.
Yeah, no, it was
That was bottom.
I spent a
Why
good
look at my
like,
chest for you?
Why are you opening it up?
I didn't realize it was. I thought one was there. She wouldn't. It's not like it's down here.
You had a taco meat show?
Taco meat? You call this taco meat?
That's what my uncle always calls his chest.
Taco meat? That's disgusting. I feel so ashamed.
I'm so confused.
I didn't realize that his bottom one was a button. And he was like,
Yeah, I was like saying, Aaron, you're showing a lot of chest.
It's like when you're looking at it.
You had your
chest right
You
here.
had your sweat all the way
Yeah,
up.
mine's all the way up. Gotta go with the air tie.
Unbutton one of them.
Just leave.
Are we all, everyone set? Hello, everyone. I'm Carter Taylor, an undergraduate studying computer science and applied mathematics at SMU. Yes. And I'm here to present on my proposal on star-based centrality metrics for determining critical nodes in interdependent networks. My advisor is Dr. Christos Vokiatsis, sorry. And I will explain what all of these words mean in due time. So just to give a basic outline, I'll start by introducing the problem, giving some definitions for the field, motivating the problems with some examples, move into like formally defining the question that we're trying to answer, and some proposed strategies, some goals for what we're looking to get out of this. And then I'll talk about some of the important literature, some of the things that this is based off of, and some of the other researchers that have tried to solve this problem before. And then I'll go into sort of how we're planning to implement this. So in Italy in 2003, there was a massive blackout, knocked out power for about half the country for a number of days in some cases. One of the 10 worst blackouts in history in terms of people without power and monetary costs. And it turns out it was the result of a single fault in what was not even a power station. See, the way that Italy's power grid is set up is there is sort of a power grid, and then there's a communication network that sits on top of it. And some facilities serve both. So there will be a power station that is attached to the communication station, and they rely upon each other. The power station feeds power to the communication station, which sort of controls the power station. And in one of these facilities, this one here marked in red, in fact, the communication station had a fault, and that led to the power station going out. And if you follow this, that led to a lot of other power stations being disconnected from the larger grid. And then over here you have about half the country, everything in red, without power. And this was a major problem. Like I said, lots of dollars, lots of people without power. So what we're trying to do is find a way to predict the nodes in such a system that could lead to this this sort of what we call a cascading failure. So just to set up some definitions for you, what we're looking at is sort of a subset of what's called graph theory, which focuses on graphs, which are basically mathematical constructs that model relationships, right? So we live in a very interconnected world. We have power stations, which are connected by lines that form power grids. We have cities that are connected by roads that form infrastructure networks. We have people that are connected by interpersonal relationships. These form like social networks. And this is sort of a strategy to formalize that and be able to deal with it more mathematically. And then here's just sort of a basic example of a graph, just so you can sort of see what it looks like. And some of the terminology that I'll use to refer to graphs are nodes. These are the sort of objects that are in the graph. Edges are the connections, and components are groups, connected groups in the graph. So then another thing we have to define, in particular in the case of, say, Italy's power, is an interdependent network where you have certain elements of the graph, certain nodes that rely upon the same underlying object. Where here you have this red node and this blue node that are, you can think of those as being the same facility, where the blue node represents its place in the communication network and its connections there, and the red node represents its place in the power network. And one of the important features of these interdependent networks or interdependent graphs is that they introduce the possibility of what I was talking about earlier, the cascading failures, So if you look at, in particular, this diagram here, and you think about, say, deactivating one of these nodes. In particular, we can pick this one here. It's labeled U1, but that might be hard to see. So if we say U1 has a fault, there's a problem, it goes down also, and then as a result of that, it's no longer able to feed power to V1. So V1 goes down, is disconnected from the network. That separates off this entire group from the larger communication network, and those are no longer able to function because they're not connected to the larger network. And then as a result, all of these components are no longer active, and their corresponding power stations are then cut off, which causes, as you can see, even further damage to the power network. This is essentially what happened in Italy in 2003. And we're trying to predict which nodes are going to cause problems in that way. So to sort of put it more formally, we're trying to develop a metric by which we can score nodes based on their criticality and try to be able to pick out the most critical nodes in a network, the ones most likely to lead to a cascading failure. And in application, this allows us to, or this clues us in as to which nodes we want to, say, fortify. If it's like a if it's an infrastructure network like power or something like that, or which ones to try and interdict if it's, say, a criminal network, and we have individuals across multiple criminal networks like that. And then I included this plot here. I apologize if you can't see it so well in the back. But one of the key features here is it sort of describes the failure dynamics of interdependent graphs. If they're sort of targeted based on criticality. So you have a couple graphs here in which nodes are being removed based on their criticality. Most critical nodes being removed first. And then at a certain point, around 20 nodes in this case, they're weakened to the point at which the largest component, which is your sort of y-axis here, their largest component crashes and is essentially zero from that point on. This represents sort of the cascading failure actually occurring in that graph. And that's sort of describing the dynamics of what it is we're looking out for. Now, as it turns out, it is possible to find the maximally critical node in a network, but that problem is NP hard. You can do it rigorously, but it will take something like the lifetime of the universe to actually finish for particularly large graphs. So we're trying to develop an algorithm that does it in a reasonable amount of time. And so for that, we need some sort of stand-in for criticality, something that we intuitively expect to be close to criticality, or at least be somewhat correlated with it in the nodes that we pick out. So we're looking at various centrality metrics. Different centrality metrics will count things like how many neighbors a node has, how many paths between other nodes it has, or how many paths between other nodes the node in question lies on, things like that. And in particular, the one that we're looking at here is what I'll call star centrality for the time being, which looks at induced stars in graphs about a particular node. So an induced star is basically just a set of neighbors of a particular node that don't have any mutual connections. So in this case, if we picked, if we were looking at the black node, we could say pick the red node here and the green node here as the neighborhood, the induced star that we're looking at. Or we could pick the blue node and the green node, but we could not, in any configuration, pick the blue node and the red node together, because those have a mutual connection. And then star centrality just looks at how many neighbors the induced star has, and scores the node based on that. It looks for the star that has the most neighbors, and that's the metric that it uses. That's our strongest candidate at this point. But as we review literature more, other candidates may appear. But this is sort of our starting point. And then this is some of the literature that this is based on, that our present work is based on. This first paper here appeared in Nature in 2010. It's helpful because it sort of defines interdependent networks rigorously, and it describes their failure dynamics, where you sort of get the cascading failure, and how to predict when that might happen, based on the probability of connection between nodes. The second paper here, more recent, is currently in print, actually. This proposes the star centrality metric that we're looking at. Sort of provides like a first candidate starting point. And then this third paper is an IEEE paper, actually, and that focuses more on the applications. And that actually attempts to solve this same problem, but just using different methods. They use weighted adjacency matrices in that, and sort of repeated multiplications of adjacency matrices. And they also use a different basic stand-in for centrality, or for criticality. They use sort of a degree centrality notion. And then just some basic implementation stuff. We'll be using Python, and we'll be using it with NetworkX package for building graphs and things like that, and the Python API for Neuro, which is useful for solving linear programs. And in fact, the linear program sort of formulability of certain centrality metrics is why we want to pick star centrality, because it has a nice formulation as a linear program. It can be maximized easily in that sort of format, and then we can sort of hand that off to Neuro or other solvers and simplify that process a bit. And then these are sort of references that I use, and thank you for your time, and I'll open the floor to questions.
Do you have like a concise definition of star centrality? What is star centrality?
Sure. So I'll go back here. Star centrality is the sorry. Let me try to formulate this mentally. It's the maximum number of neighbors to a periphery of nodes that have no mutual connections, but which are also neighbors to a central node. So if we're looking at a particular node, an induced star would be a set of its neighbors that don't have any mutual features. And then the centrality just finds the star that has the most outside nodes as neighbors to the induced star.
So you could write down a concise definition of it mathematically, can you?
Sure. Is there?
No, not here, not here. I'm just saying, would that not be a important exercise for you to accomplish?
Yeah, well,
To implement your algorithm, or has it already been?
yeah, it's already been done, and we've tested this already, even extending this to interdependent graphs, using Gurobi and using linear programming. We've come up with a formulation that's that solves maximum star centrality, but it's a little lengthy. If you want to see that, that's in the proposal.
So another question I have is that, can you go to the other slide you have about the two layers of the network? Now, why don't you think about is a edge important as well? In terms of a critical edge as opposed to a critical node?
Yes. Yes, we can think about edges in terms of criticality, but in this case, since we're looking at the ability to say like fortify a particular facility in the case of like infrastructure, or interdict a particular say criminal in the case of like a criminal network. In those cases, it's easier to work with the node, and perhaps more relevant to work with the node than the edge. But yes, we can also look at like at different cuts, like maximum cuts, K-cut algorithms, things like that, for determining criticality.
I may be misunderstanding. Are you going to work with a particular data set to create or to run through the star centrality or house?
Yeah, we'll have some data sets that we'll work with. That's, I guess in this particular case, the data set in question is I guess isn't the most relevant thing. We're mostly focused on developing the algorithm, and then we'll just have some test cases basically to see how it sort of measures up against other measures of criticality.
So is there going to be any way you check for how well your algorithm performs, like how well it identifies the central nodes and how well it identifies the ones that are more likely to cause the cascading effect?
Yeah, actually, if I go back here, I apologize for how small this is, but one of the things that this paper did to measure how effectively an algorithm identifies a critical node is they saw how many iterations, how many removals it takes of the maximum critical node, or the maximally critical node, before you experience this sort of discontinuous drop in the size of the largest component. And so we'll use a similar strategy. Any more questions? It's sort of meant to be different. Yeah, so it works for both.
Okay, so my name is Haley Muller. I'm a rising senior at Mississippi College studying kinesiology with a minor in biology. And I'm doing my project this summer on a model of the diabetic foot biomechanics. And I'll be working with Dr. McCullough throughout this research. So just kind of an outline as everyone else has done. I'll go through an introduction, a little bit of background information, state the problem statement, the goals for my research, the key papers that I'm using for the research, and kind of how I'm going to go about conducting the research. So some background information. Diabetes effect on America. So I'm sure you guys have all heard of diabetes, know kind of what it is. Diabetes affects over 30 million people in the US, which is over 9% of the population. So that means that in this room right now, there's probably at least 2, maybe 3 people that either have diabetes now or will develop it sometime in our lifetimes, whether that's earlier on or later on, just depending on the type of diabetes. So what is diabetes? Diabetes is a condition that affects how the body responds to insulin. So insulin is produced in the body by the pancreas and secreted when there's a rise in blood glucose levels in the body. The insulin goes to the cells and signals the cells to uptake the oxygen from the blood and bring it into the cells. There's 2 different types of diabetes. There's type 1 diabetes, which is considered juvenile diabetes, which is typically something you're born with or you develop very early on in life. In this type of diabetes, the body does not produce insulin. So there's just a problem in the pancreas. There's no insulin production, so that when there is a rise in blood sugar, the body can't uptake it into the cell because there's nothing signaling the cell to bring it in. Type 2 diabetes is often called adult onset diabetes, which is when the body builds up a resistance to this insulin. So there is insulin being produced in the body, but the cells just don't recognize it. So even when the blood sugar does increase, the pancreas sends out insulin and it goes to cells, but the cells just basically ignore it because they're resistant to it. Nothing really happens. So the rise in blood sugar in the body can cause lots of problems. We're looking at the problems that it causes, particularly in the feet, and how it changes that. So the excess sugar will bind to proteins in connective tissues in the body, which are things like ligaments, tendons, fascia, and different things like that. So it will bind to the proteins in those, and it will convert the proteins to what's called advanced glycation end products, or AGEs. And these AGEs stiffen and change the properties of those connective tissues. So instead of having like elastic tendons and ligaments, those parts all stiffen. Another thing that the increased blood sugar can do is that it can damage small capillaries that are in feet, hands, basically anywhere in the body. And if this is a capillary that supplies blood to a neuron, the neuron will die as well. And when the neuron dies, this is a condition called neuropathy. So neuropathy happens because the neuron no longer has a blood supply, so it can't function. There's 3 main types of neuropathy that happen as it relates to the extremities. One is sensory neuropathy. This is when the neuron that no longer has a blood supply that's being affected is a sensory neuron. So let's say, going back to the foot, it means your foot, you kind of get that pins and needles feeling, like if your foot falls asleep, it's that feeling, but worse than all the time. So you can't feel your foot. You can still move it, you can still walk, but if someone were to come poke you with a needle, anything, you wouldn't be able to tell whatsoever. The next type of neuropathy is autonomic neuropathy, which affects the autonomic nervous system. In the cases with this in the foot, it will decrease the sweating that your foot does, which can lead to dryness and irritation and cracking of the skin on the feet. The last type of neuropathy is motor neuropathy, which is when the motor neurons are affected. So in this case, you can feel your foot, you can figure out like when someone's touching you, but you can't move it. The muscles are not able to contract or anything like that. When these different types of neuropathy are all combined, it can lead to a condition called Charcot Foot. That's kind of a picture of what it looks like. The bottom of the foot is deformed there. Charcot Foot occurs when the muscles, tendons, ligaments, and things like that are weakened, and the natural position of the foot actually changes. When this rocker bottom occurs, it can increase the plantar pressures, which is the pressure on the bottom side of the foot, which can lead to ulcers, which are like really bad sores. And if these ulcers become infected, it can lead to gangrene, which is the death of the actual tissue. So the tissue, skin, things like that on the wall of the foot have died and no way for them to come back. And if that continues to spread throughout the foot, it can lead to amputation. So this is why some people with diabetes end up having to have foot amputations. So the problem statement is that midfoot bone displacement due to the altered mechanical properties of tissues in the diabetic foot is not well understood due to the lack of specific midfoot modeling. This is a problem because without understanding this displacement, there is no way to predict catastrophic events like the collapse of the arch. So these neuropathies and all the things that diabetes cause the bones to shift, which we saw in the last picture of that rocker bottom. And we know that the bones move, but the exact mechanism of how and why exactly they move is kind of unknown. So that's what we're going to be looking into. Most of the models that are created for diabetic foot have to do with the plantar pressure on the bottom surface of the foot, which really just focuses on what causes the ulcers and how to prevent that. But what we're going to be looking at is the arch of the foot and the midfoot, which is the arch, and what causes the bones in there to actually displace. So the research goals to develop a simple model of the bones and ligaments of the midfoot. We're just keeping it simple, it's just a semi program, so we're just looking at the midfoot bones, which are outlined in blue here. There's 3 regions of the foot: the forefoot, which is the toes, and the bones, the metatarsals, which make up the long bones of the foot, the midfoot, which is outlined, and there's 2 bones behind that called the hindfoot. So we're just looking at the midfoot, and then we're going to add in a couple ligaments as well. But we're just going to keep it simple with bones and ligaments. And then we're going to place loads on these models that simulate just a person standing and see how the bones move with the load. So your foot is in a different position naturally. If you pick it up, there's no pressure on it, it's nothing, so the bones are going to be in a relaxed position. But when you stand and apply pressure to it, the bones shift a little bit. That's normal, but in a diabetic foot, they shift more, and we're going to try to figure out kind of how the changes in properties of the ligaments cause that. So some of the key papers, this one is a 3-dimensional anatomical detailed foot model. And in this article, these people set out to build an anatomically correct model of the foot. So they took a bunch of MRIs, X-rays, things of that nature to see where all the bones were and how to model it. Most models figure out where each bone is in the foot, but this one uses one bone as a reference. So it uses the talus bone, which is right under your leg bones. It's what connects your tibia and fibula to your foot. So it uses the talus bone as a point of reference, and it describes every other bone in the foot as it relates to its position relative to the talus. To do this, they use a Z, Y, X coordinate system. So for the first metatarsal, this was its coordinate. So the Z, the 89.6, determines it's the long axis of the bone. So in the first metatarsal, if this is it, it's just kind of its rotation around. The X, which is the far one, is the longest moment of inertia. So it's rotation around the Z. So here it just kind of rotates this way, and then the Y is the cross product between the X and the Z. So for this one, the first metatarsal, the 89.6 is a counterclockwise rotation. The 8.55 degrees is 8.55 degrees of plantar flexion relative to the talus. So you can see here, this is the first metatarsal. It's angled a little bit, points a little. That was touchscreen. It's angled a little bit more down in the talus. You can see here, it's more straight, and then it gets the first metatarsal points down more. And so what this paper determined was that this degree right here is 8.55 degrees. That was the difference. And then the 15.5 degrees is 15.5 degrees of external rotation relative to the talus again. So you can see here the talus points more inward. If this is a right foot, it points more inward, then the first metatarsal is going to point outward more. So for our research, this gives us a way to measure the movements of the bones. It helps to integrate, get to do it relative to other bones because it's the easiest way for us to see it in our model. So we can see when we add the loads to the model and the bones change, we can not only measure how far they move, but also how they move in relation to the other bones and how the angles between them change. This paper, the diabetic foot ulcerations, biomechanics, Charcot Foot, and total contact cast. This paper focuses on the different types of neuropathies, the mechanisms that cause the neuropathies, and then the things, how Charcot Foot manifests itself mechanically in the feet. So the mechanisms it lists for the Charcot Foot, it gives 2 different theories as to how the neuropathies create Charcot Foot. And the first one is a neurovascular theory, which states that the increase in blood supply to the foot caused by autonomic neuropathy actually leads to bone destruction, which debilitates the foot. So the increased blood will start to break down the bone tissue, which causes the foot to collapse because there's just no bone there to support it. And then the other theory it lists is the neurotraumatic theory, which states that the loss of protective sensation caused by sensory neuropathy leads to someone not being able to feel trauma in their foot. So if you have sensory neuropathy, you can't feel your foot. If you break a bone or if a bone gets dislocated or anything like that, you can't tell because you can't feel your foot, so you just keep walking on it. Well, over time, that's going to cause lots more problems than just that one single broken bone. It also, in here, it also lists what actually happens in your feet due to Charcot Foot, and some of those are Forefoot Supination, which is when the ball of your foot and your toes start to roll towards the pinky and supinate, is what that's called. And that's due to damage in the soft tissue, which is caused by the AGEs and the tightening and stiffening of those connective tissues. The next one is Forefoot Abduction, which is when your hind foot and midfoot are lined up properly in a neutral position, but the balls of the feet actually start to turn outwards. The foot's no longer pointing straight, and it's not an ankle problem, it's the foot itself actually shifts. The next two are hindfoot medial translation, which is when, so the calcaneus is the heel bone, and the talus is the bone that sits right on top of that. It's supposed to sit like this, kind of, right on top. They're made to fit like that. But in this medial translation, they actually get shifted apart, so it doesn't sit directly under it. That puts lots of unnecessary strain and stress on all of the tendons, ligaments, muscles that surround it. And then Varus Calcaneus is when the calcaneus, or heel bone, gets inverted. So if it, when combined with medial translation, it kind of shifts like that, as you can see in the picture, which is another thing. It puts your ankle out of improper position, which is bad for the muscles and tendons and everything in your ankle, and also goes up to your knees and hips as well due to the added stress. And then the last one, Charcot Foot, is the rocker bottom, which you already saw. It's like an inverted arch, basically. Your arch is supposed to go up in your foot. It helps spread out stress. But the rocker bottom, the bones all collapse, which is caused by the weakening of the muscles everywhere. And then the next paper is a comparison of the performance of hexahedral and tetrahedral elements in bone, soft tissue, finite element models. So we'll be developing a finite element model of the midfoot area. And this paper talks about the different elements that they used in their model to represent the soft tissue. So for bone, they used rigid objects that weren't able to move, but they tested linear hexahedral, linear tetrahedral, and quadratic tetrahedral elements to model the soft tissues. So you can kind of see the difference. The hexahedral is a square, the tetrahedral is like a three-sided pyramid, and then if it's linear, it has nodes just on the corners. If it's quadratic, it has nodes on the corners and in between each corner. The linear hexahedral is usually a good one to go based off, but it gives very smooth and uniform results, but it takes a long time to run, and it's very complex to make. The linear tetrahedral is super easy to make. It doesn't take long at all to run. However, its results typically aren't uniform and smooth. It kind of gives, there's lots of gray areas in the results, and it's hard to tell if that's actually going to be good. So when they tested this one, they saw that the quadratic tetrahedral gave results very similar to the linear hexahedral, which is known to have very smooth results, but it took a lot less time to run, and it was much more simple to model as well. So for us, this is a great paper to go off of, knowing that we're going to be creating these ligaments. So we'll definitely be starting with the quadratic tetrahedral. It'll be simpler to model, and it gives good results, but also that's where we'll be starting. If we need to modify it, we will, but it gives us a great starting place. So methodology, approach tools. We'll be using finite element method to model the displacement of the bones and see when they move. Finite element method takes a very complex problem, breaks it up into smaller parts, solves all the smaller parts, and then uses the answers to all the small parts to give an estimated answer to the big part. In short, that's kind of how it works. I haven't learned this yet before the summer, so I'm still kind of learning myself as to how this all works, but that's something I'm working on. We're modeling the midfoot region only, so in this picture you can see the green bones on the midfoot region. This includes the navicular bone, which is right here, the medial cuneiform, intermediate cuneiform, lateral cuneiform, and the cuboid bone. We're also going to be including 3 ligaments in our model. There's actually many more in that area of the foot, but just to kind of keep it simple, we're going to use the 3 main ones, which are the plantar cuboid navicular, which runs from the edge of the cuboid here to the edge of the navicular bone. there, and it goes underneath the bottom of the foot. And then there's also a dorsal cuboid or navicular ligament that runs from the same edges, but it goes on the top of the foot instead of through the bottom. And then there's the dorsal cuboid, which is on the top of the foot, and it connects this bigger bone here to all three of the smaller bones. So those are the three ligaments we're going to model as well. We'll model the change in ligament properties to reflect diabetes. So we'll first create the model using rigid elements for the bones, and then the quadratic tetrahedral for the ligaments, and we'll first make the elasticity match what a healthy ligament should be and how it should stretch and mold. And then we'll run the simulation with that, and then we'll go back and alter the elasticity construct of those ligament elements to model, to have the elasticity match what it really is in a diabetic foot. We're going to build upon existing models. There are models that are already out there of the foot, so we're going to try to import those and use some of those. We might have to add ligaments if we need to, or take out bones that we're not using in our simulation. We may end up having to build one from scratch. There is one of Dr. McCullough's grad students working on a model right now that we're going to try to use. So we're going to try at first to see if we can use these existing ones, but we may end up having to build it from scratch and use all our own elements. We'll be using FEBio to run all the simulations. Everything is done through FEBio. There's a very user-friendly interface to create the model itself, and then it's run through their finite element analysis model, and then there's a way to view it at the end to see exactly where the bones are displaced. And to measure bone displacement, we'll measure the displacement of every bone from before the load and after the load was put on it for the healthy foot first. And then we'll do the same thing with the diabetic foot, see where the bones started, where the bones ended, and then we'll be able to compare where the bones ended for the healthy foot, where the bones ended in the diabetic foot, compare those two, and then we'll do the same thing with the angles between the bones, preload, post-load for healthy foot, diabetic foot, and we'll be able to compare all that data. These are just my references here. All the key ones are listed there, and also some other ones that are helping us in our research.
Is there a year on the last paper that you said was a key paper?
No, I couldn't find one that was listed. It wasn't on the document, the PDF document that I was sent.
So you cited another paper that was key. Is that the one that has the model? The first of the three that you had in your slide set? Is this the one that gives you your model?
They created a model in this one using every single bone in the foot.
Oh.
And they used the method of using the 3 coordinates to place all the bones. So yes, there is a model in this one that they created. They gave instructions as to how.
Is it what you're starting with?
We're going to be starting, no, that's not the one. We actually haven't found the exact one that we're going to start with. We haven't looked into that yet. But there's some that people like post when they finish them using FEBio. So we're going to try to find one. Dr. McCullough said that there are some out there, and we just haven't found those yet.
FEBio is the tool, is it? Is that the software you can
Yes,
use?
that's the software.
Is there any code you're going to write?
No, it's all part of the FEBio. We don't have to write any code. Once we, there's 3 parts of FEBio. There's the first part, which is where you create all the elements, so that's very user-friendly. There's no code related there. And then to run the simulation, you just tell it to run it, and it does it all for you. There's a little bit of code, but there's like just basically 10 different lines of code that it uses. And then it gives you an output and shows you what happens when you run the simulation.
So you mentioned that in your model, you're only going to be modeling the midfoot.
Mm-hmm.
Do you lose any important information by leaving out the sort of context of the forefoot and the back foot?
Potentially, yes. It's a lot more complicated to model the whole foot because of how long it takes, so potentially, yes. What we're focusing on is the midfoot because that's where the arch of the foot is. So the arch of the foot, when that part collapses, that's what causes Charcot Foot typically. So yes, potentially, there definitely would be, but this is just kind of a starting point for us, as it's just a 10-week program. But yes, there definitely could be. Any questions?
Thank you.
Good afternoon, my name is Adasia Nelson. I'm from Jacksonville State University. And my project is on combating cognitive bias using visual analytics. And my mentor is Dr. Yang. This is an outline for my presentation. I'll begin my introduction, and then I will go into my research problem statement, then my research goals, my key papers, and finally my methodology. Food insecurity is a problem that affects people worldwide. In the world, 815 million people struggle with food insecurity, and in America alone, 1 in 8 people will struggle with food insecurity. Food insecurity typically falls into 2 categories. There is low food security and there is very low food security. Low food security typically means that people have access to food on a regular basis, but it's neither desirable nor healthy. So this would be a family that gets by on fast food because it's cheaper and more accessible. Very low food security is when a person or individuals do not have access to food on a regular basis, or they eat below what is the healthy amount for them. To combat food insecurity, food banks were created. They initially started with food being given from the back of trucks, but they have grown exponentially since then. The largest food bank network in America is Feeding America. It fed 46 million people in 2016 alone, and it did this through its use of 200 food banks and over 60,000 food programs. One food bank is the Food Bank of Central and Eastern North Carolina. This food bank feeds 34 of the 100 counties in North Carolina, and it does this through its 6 branches and over 800 partner agencies. Partner agencies are places like soup kitchens or group homes that get the food directly. And in 2014 alone, it distributed over 57 million pounds of food. Cognitive bias is a mistaken reasoning, evaluating, remembering, or other cognitive processes, and this is often occurring as a result of holding onto one's preference and beliefs regardless of contrary information. As you can see by this image, there are many different types of cognitive biases. An example is choice supportive bias, and this is just when we make a choice and of course we're going to support this. An example of this is seen when people defend Apple versus Android. You will most likely defend the product that you own rather than say, yes, I made an error in my decision. Another example of cognitive bias is confirmation bias, and this is when people have pre-held beliefs and they only filter in information that confirms this belief. An example of this would be if I were a cat owner and I was trying to motivate my friend to also become a cat owner. I may search things such as benefits of having a cat photos, different things that would ultimately yield me positive results regarding cats. And this is bad because I failed to look at impartial sources. Visual analytics is a human-centered process of combining our visual intelligence and analysis techniques with interactive technology to get relevant information out of data. Visual analytics allows us to interact with data at the same speed as our thought processes. And if visual analytics are created to work in synchronization with the decision-making process of humans, they can aid in curbing the presence of cognitive bias. So how does this relate to my research? Well, executives at a food bank are often overloaded with information. They have potentially very large quantities of data that they have to look at regarding their food banks. And they typically look at this in spreadsheets that may be very lengthy. And from these spreadsheets, they have to determine trends. And this may cause them to fall victim to cognitive biases because it is difficult to take in that much or a lot of information from a spreadsheet. And this is where visual analytics comes in. This will allow them to have interactive visualizations of these facts and figures so that they can make informed decisions. And these decisions may be about where they should distribute their food or the amount that should be distributed in certain places. My research goal is to curb cognitive bias through visual analytics and aid food banks in making better decisions regarding the use of their resources and do this impartially. These are some of the key papers that I will utilize in my research. The first one is the Household Food Security in the United States in 2016. This was a report that was done on food security in America in 2016. It ultimately found that there was no significant change in the state of food insecurity in America from 2015 to 2016. The second paper is Visual Analytics Approach to Combat Confirmation Bias for a Local Food Bank. This was conducted here at NCAT, and this ultimately found that through the use of visual analytics, people did have higher confidence in their decisions in contrast to from spreadsheets. The third paper is using visual analytics to support humanitarian belief. This paper focused mostly on constructing visual analytics and how this would be best utilized for humanitarian relief. And the last paper is interactivity in visual analytics, the use of conceptual frameworks to support human-centered design of a decision support tool. This paper discussed how for visual analytics to be best utilized, it should work in cohesion with the human's thought processes. Now, methodology. For this project, I will work mostly in Tableau, and I'll be building forecasting models using this. Tableau by default, it uses exponential smoothing, and for my forecasting, I'll be building a time series model. And this, I may build models for things such as the amount of donations that the food bank receives over a certain period of time. And as I said earlier, Tableau uses exponential smoothing by default, and this means that it gives more weight to more recent data in contrast to older data. And a type of exponential smoothing is winters, and this just takes into account seasonality, which is beneficial if we're doing it over a period of time. For this project, I'll be using a between subject design. So a group of participants, ideally 8 to 10, will be taken, and they will essentially be split in half. Half of them will use visual analytics, and the other half will use the spreadsheet. And from this, they will be asked to forecast data. And the between subject design just means that they will be split in half, and this will aid us in making the comparison between them. For statistical analysis, we will use the t-test, and we will be doing it unpaired. The t-test just allows us to see if the difference in the accuracy of their predictions is significant or not. An example of this would be if I were to flip a coin and you were to flip a coin. If I were to land on heads 51 times and you were to land on heads 49 times, is this significant? The t-test would allow us to see. The results. The results of the study can test the hypothesis that information visualization can help combat cognitive bias apparent in the decision-making of individuals and increase their confidence in their decisions. And these are markers. Any questions?
So that second key paper you said, the one that was done here at A&T, so is your research kind of like an extension of that?
Mm-hmm.
Okay, cool.
For their research, they didn't utilize the t-test, and we will this time, so I'm just gonna see how that affects it.
Tell them you should be on the next publication because you're about to help them out.
Go back one slide and talk about the second part of what that says. The, what?
This or the,
Yes. So, no, that's not what I'm thinking about. Are you going further back? Go forward.
this.
Keep going forward. Keep going forward. There you go. Then increase the confidence in these decisions. What does that mean?
Well, it just means that they feel confident that they got a good sampling of the information, or they have a good grasp on the information that was presented, where like in the spreadsheet, they may feel that they didn't necessarily look at all the facts and figures. When they look at the visual analytics for the information presented to them, they feel more confident.
So you're assessing both in terms of how good of a decision they make and how good they feel about the decision.
Yes, sir.
Can you go to the next slide? I think I'm not sure which one it is. Oh, no. It's one of the methodology slides. Okay, let's keep this one. No, the next one. Next one.
Next one.
Yes. So when you say it's between subject design, can you walk us through your methodology? Let's say you start your research on Monday.
Mm-hmm.
What are you going to do first? What are you going to do next?
Well, first we would have to receive data from the food banks, and from this we would compose visual analytics and this is what we would test eventually. We would, of course, take visual analytics, and this would be used to forecast data, and then we would find participants to participate in the study, and half of them would make forecasts based on the spreadsheet, and the other half would forecast based on visual analytics that we create.
So even visual analytics could be, presented in multiple ways, right? So is that an issue, or it could be just one way of presenting visual analytics?
I think we would try to compose many different ones and see which ones we think would work best in the situation.
So what's the significance of this between subject design?
This just allows us to see impartially, or relatively partially, whether the spreadsheet or the visual analytics would yield better results. Any other questions?
Very good. We have another 7 minutes. We can take a 5-minute break, maybe. Start close to 3 o'clock.
Oh, no. Because it duplicates the stuff. So if you just give it a you can, if you want to put it to my computer or something, just put it right here. That's what I did. So it's like, I was standing there, something I had in my computer facing me. So I click on the slide for that and just like walk up. So I press the next page.
This time, refill. Like every 4 hours, you get down and something.
Yeah. So walk right into it.
Was that
Representative.
Yeah, no, I was gonna do that. I'd rather not. Yeah. Like, questions to like read what, like, data.
How was the graduation?
I get data. Hey, How big surreal. Like, I graduated, my son graduated the same year. But I think that's what they used to do. So like I was trying to enjoy. So when it was over, where you were like, everything's over here. If you go back last night, I just wanted to last night. After that, taking to get a haircut. That was really good. You see that pretty much everybody is doing the same thing you do, trying to speak as much as possible, getting our way from sit down. Just trying to really common. Very good. Like that's how it works. The very first time you have to be research, the very okay. Yes. You don't have like everybody under there. Okay. Now everybody like got like jobs, everyone graduated, and then on Monday, you graduated, hopefully you'll be 100% on Monday. Right? Because we need to now. I was just like,
my advice are pretty nice. It's kind of nice.
Yeah. I didn't know you already met with him. Okay. He's very kind, isn't he? Yeah. So we met by name usually. Yeah. Basically, he was telling me sort of through his culture. She explained. Sort of the way. Yeah, manual. We want to make sure she got successful. I think that's what he had in mind. We're going to build some of the things you need. Okay. Good. Yeah, that was good. What? It's like you see that you guys the same thing. Like they have like to get into all your concepts and that. So you spoke to them. I was explaining. No, I know. I was looking at the time because I was like, let's do okay, ask you the question. It was a thing. So then Cameron just asked a question, he'd be like, you want to get punched in the throat? I'll give you 10 things. And they'll be interesting. I just see you just like jump over. Imagine if you're doing it rather than something like this. But the goal is like, see what we know. Cameron, we gotta do some jump and stuff today. There's more of that light work. Oh, yeah, you're going to do set up your it's probably complex. Yeah. You invite me to a show, and I will do that. I'm still like a little stage. Okay. Yeah, just tell me I'll do it at 5, so like as soon as I set mine for 5. Oh yeah. Okay. You set a reminder. I set a reminder to get Eric my parking pass. It's a long term. Not my one for you, but my parking pass for home, he's going home, and that's gonna be parking pass. I'm actually just gonna use it to go back home and park at his apartment. And then visit people at state. Yeah. I know when it was at state, no one's in school. Yeah, dude. Everybody I know is going. At least I know worries in my life.
Let's see.
Just be better.
Okay, so answer. Yeah. Matt.
There's something called my math lab. It's the same thing as like my econ lab, but that's not the same thing at all.
But look, you do math as a lab. So
You don't just do math.
So the first thing I'm gonna think of is math.
You don't have to do math. You can do things that are math.
Okay,
You can either make a game where you like play cards.
When Kabaddi taught us, who was doing math?
I had a
In the back.
I use MATLAB to make a program for gambling. Granted, it was a project, but
yes.
But still.
2% chance.
What?
It was so boring to play. I was like, just put me all in every time. Just keep going until I lose.
I did a project in Java. Like how to create a graph for user interface, but it's being called that search out of we spent weeks, we had 2 weeks of the time, spent 9 days trying to answer this everything's online.
Yeah, I really wish I had like checked it first semester. I could have probably checked this for.
I'm like so long. So good evening, my name is Sakina Patterson. I am a rising junior at Jackson State University in Jackson, Mississippi. My mentor is Dr. Sweet, and I got help from Divine the Back. And my research topic is optimal route generation for people with disabilities using MATLAB GPS. My outline, first the introduction, just giving some background on my research problem statement, my research goals, key papers, and my methodology, and my approach to how I'm going to finish out research. Introduction. Transportation is a very important component for all ages. We use transportation to get to work, get to or from to the house, to stores, to school, and the list goes on and on. Before GPS, it was ideal for you to know where you was going before actually getting in the car to go. And that just limited you having to call and get directions, be on the phone while you were driving. It's just a bunch of danger going along with that. And but however, the discovery of the GPS allowed the life of transportation to be a lot easier. What is GPS? GPS has its origins with the Sputnik area, when scientists were able to track the satellites from the ship and radio signals known as the Doppler effect. Today, GPS is a multi-use science-based radio navigation system, and it is owned by the U.S. government and operated by the United States. Since the invention of the GPS navigational system, people have been able to easily find quick routes to destinations that they have visited. The problem with this, though, is that elderly and disabled people often find difficulties in traveling. Even though GPS has made life easier and has a positive impact on today's society, it still brings challenges to those who are physically disabled and suffer certain disabilities. Certain routes are not safe and are also very inefficient for those who are elderly and disabled, of course. If elderly and disabled are provided with routes that can safely, accurately, and efficiently guide them to their destinations, then the difficulties and dangers associated with traveling would significantly decrease. And this is where route optimization is put in place to help those disabled. And what is route optimization? Route optimization is basically the process of dealing with finding the shortest path between two places that is most beneficial for the driver. This is why we're focusing on route optimization to make life easier and more efficient for those who are disabled and elderly. This brings me to my research problem statement. Is it possible to optimize route generation for those who are disabled using GPS and MATLAB? Research goals. Our goal, of course, is to create a GPS navigational app for elderly and disabled mobile users to optimize route best fit for them. Android Studio will be used and other software applications to develop this app to optimize the route, which will be beneficial to mobile users. For example, avoiding difficult turns for people with arthritis. Arthritis is a disease that mostly older people, but it's not subjected to just them. Some younger people get arthritis in their hand as well, and it causes their bones to be tight, have tension in them, and very stiff. And everyday drivers experience having to take left turns, right turns, U-turns, and etc. And each turn has its own set of difficulties. And what we would do or try to do during this research is to make sure that we optimize the route for those who have arthritis, to make sure that they avoid turns like that. Like, let's say McDonald's is right here and you're driving, but the only way to get there is you have to make a U-turn and come back and then go into McDonald's. We don't need them going to that McDonald's to put them in ways of hurting their hand even more or not being able to turn to complete that full U-turn. Keeping them safe from adverse weather conditions. I know back home, the bridges tends to get slippery when wet. And just to keep them out of harm's way, just easily optimize the route to make sure that they do not cross over any of the bridges or just make a detour around those type of bridges or other landscapes that might affect their car or any other transportation that they use to get around. Avoiding interstate highways for people having slow reaction time and reflexes. Of course, when you get on the interstate or you get on the highway, things tend to speed up. I mean, the speed limit is 60 or 55 or 65 or 75, depending on where you live, as opposed to inner city routes where it's like 35, 45, which is more feasible for people of older age. So just basically making routes where it's more inner city than straight highway or straight interstate to keep them safe. Because as you get older, your reaction time slows, your reflexes slows down, etc. Also, choosing routes with proper sidewalks, less traffic, and pedestrian traffic signals for wheelchair users. Cars and buses are not the only way that most elderly people get around. Some people just have wheelchairs. I know in small cities or states like Mississippi, Hattiesburg is where I'm from. It's a smaller city compared to New York or something. So some older people just use their wheelchairs to get around. But you don't want them to put in their GPS that they're trying to go to the grocery store and it sends them down a route with no proper sidewalks for them. So they're on a street with no sidewalks putting them in harm's way. Also, pedestrian traffic signals, so when it tells you, when to walk and not to walk. Let's say they have to cross the street. Sometimes we jaywalk, we can run across the street real quick to make sure we don't get hit by a car, but we want to make sure that wheelchair users actually have a place where they can cross the road safely instead of having to roll out and try to cross the street with no, pedestrian traffic signals. We're also putting them in harm's way, and just less traffic, less prone to accidents, don't get hurt. Another goal, multiple destination route optimization, just being able to put two destinations in at one time and the GPS find a more efficient route for you to go, save less time and more beneficial to you. And also to successfully transfer our MATLAB code to Java or C++ because Android Studios and Mapbox, another software that I'm going to talk about, only uses those two. Key papers. The first one is difficulties experienced by older drivers during their regular driving and their expectations toward advanced driving aid systems and vehicle automation. This article analyzes the difficulties experienced by older drivers during their regular driving and identify their needs and expectations regarding advanced driving aid systems and vehicle automation. One of those difficulties in navigation is that around urban areas, like in the city, things of that nature, is often constraining for those who are mobility impaired to the urban landscape. And there is a need to provide a tailored map for individuals' mobility, in disability, for example. Just like I said, big cities compared to smaller cities. Big cities, more cars, more people, more things to hinder people that are wheelchair users or elderly drivers. So I think that's why we need a tailored map for both, just to keep them, like I said, at a harm's way. Explains the high risk that elderly people tend to face because of the lack of personalized route optimization that accommodates them as well. It brings attention to those who are physically disabled as well, just because it speaks on elderly people, but some of the diseases that it speaks on in this paper also can affect people who aren't just elderly. Like some diseases are not just prone to people who are elderly. Some people get these diseases at a young age as well. Research proposal on reviewing augmented reality applications for supporting age population. This article explains augmented reality, AR, as is helpful to making navigation systems more helpful for the mobility and impaired. And augmented reality is combine virtual information with real environment and real-time performance. And the term is so broad though, and just in general, that this paper kind of gives specifics of what augmented reality can do to support the aging population. It gives you the 6 elements of the AR architecture, which is user interaction, device, virtual content, real content, and tracking. And it serves as an innovate and develop the AR application. And it also gives a brief summary and details of each element of the architecture. Then also this Mapbox documentation, which was very helpful during our research because it gives you all the tools that you need to add turn-by-turn navigation to your apps. This is just basically to start us off on what we need to do to get us started next week. This document gives step-by-step instruction on how to start developing the app that we will use for navigation. It gives pseudocodes in Java, of course, because they only use Java or C++. Coding language are assigned to different projects in Android Studios, which is a tool set used to develop on Android, develop apps on Android devices. And then after completing these steps, it will have we'll have the basis of the map that we'll need to start on our research. And it saves time because we don't have to go from scratch to start up a map. Methodology, approach, and tools. What will be modeled? Mapping and route optimization will be modeled to first integrate turn-by-turn navigation. Dijkstra's and map constructs that will be used. Dijkstra's and A-star algorithms will be used during this research, and these are just 2 algorithms that's most commonly used for GPS navigation system computation, mainly for route optimization, which we'll be focusing on. Dijkstra's algorithm, it was conceived by Eskers W. Dijkstra in 1956, and it's an algorithm used to find the shortest path between nodes and the graph, which may represent road networks. It picks the unvisited vertex with the lowest distance calculated. Calculate the distance between each unvisited neighbors, and then updates the neighbor distance if smaller. And this is just a graph representing Dijkstra's algorithm. And basically what it's doing is just optimizing the route. It's going from 1, 3, 6, 5 and realizing, okay, it can skip node 3 and it can just do 1, 6, and 5. That's basically what why we'll be using that. Also, A-star algorithm, which is basically like an addition to Dijkstra's algorithm, and it is widely used in pathfinding and graph traversals, which is the process of plotting an efficiently directed path between multiple points called nodes. However, A-star achieves better performance by using heuristics to guide its search, and that was make it different than Dijkstra's algorithm. And that's just an example of how it looks compared to how Dijkstra's algorithm looks. Computational models that will be built. We will load maps into MATLAB, and MATLAB is a high-performance program language for technical computing. It integrates computation, visualization, and programming in easy use environment where problems and solutions are expressed in familiar mathematical notations. So after we load world map into MATLAB, then a route will be found from users' current location to their preferred location using MATLAB mapping toolbox. Next, using the same toolbox, the route optimization will be done to find the efficient route if the user needs to visit multiple locations, just like back when I was talking about the multiple location route optimization. And then turn-by-turn navigation will be modeled using Mapbox and Android Studio. Now, Mapbox is just an open source mapping tool platform for custom designed maps, and then Android Studio is SDK is a tool that enables developers to create apps for Android OS. And these tools will be used to successfully make our GPS navigation app for elderly and disabled users. Software tools use MATLAB simulators to provide mapping toolbox. And mapping toolbox is a library of MATLAB code modules and programs used for analyzing geographic data and creating map displays in MATLAB. So using this mapping toolbox from MATLAB, we will use in our research to create the map and to combine geospatial data with base map layers from multiple sources in a single map display. This MATLAB code will be converted to C++, which we can then use into Mapbox SDK. Mapbox and Android Studios are the software development kits that will be used to develop this app. And of course, the type of results do I seek to get to achieve finding the best path of navigation between multiple routes using route optimization, and basically to find safe routes for elderly and disabled users so that we can make GPS better for them as well. And those are my references and questions.
Is this designed to be like an app on the phone or like an app that'll be in cars?
It'll be I think right now we're just doing it on Android devices. So right now just like your cell phone, but probably more after eventually scale it. Yeah, scale up from there. So we're starting small.
Alright, so I don't know much about programming, but so is there a reason why you're going from MATLAB to C++ in Java, or can you just go directly to C++?
This MATLAB is easier for us.
Okay.
Not even gonna lie. So that's why we're gonna start with MATLAB and then just try to convert into Java. Java is actually more or less complex than C++. But that's really why.
No, I feel it.
So, how would you, I mean, you didn't talk about how you would find a path that's good for the aging population. What are the parameters? I mean, all the GIS data is only going to talk about distances and so on. So what are the other things that you're going to capture in the routing?
So I know finding the path, we really have to think about that. I just know that from other users being in the city or being from that city, they know, okay, well, there are sidewalks, proper sidewalks here, or there's traffic lights here, and there, because right now we haven't found out how to actually like get the satellite to detect where every traffic light or where every proper sidewalk is at. We haven't got that far. So we were just thinking of a way to make it like where they can input or other people can input, okay, well, since you're making this device for this, we'll put in, okay, well, this will be great for someone who is a wheelchair user. Here's some sidewalks, proper sidewalks on this street and on this street and on this street, or there's pedestrian traffic lights on this road. They're just like this, basically by input of other users right now, until we can figure out how to detect it using like the world map and actually being able to detect where every light and proper sidewalk is at.
So you mentioned augmented reality. We're going to use augmented reality here?
Augmented reality? Oh, you asked me what it is, or you asked me what it is?
No, we're going to use any features of augmented reality?
Preferably, we're trying to use it, but for right now, we're just trying to develop to get to that point. But that is in an overall goal.
Okay.
So I want to build up on what Dr. Ram asked earlier about, you mentioned two algorithms. You mentioned Dijkstra's and A-star. Both are really fast, but both have this thing that you only optimize for one thing, like say shortest path, or like, the fastest way to go or the cheapest way to go. But the way I see it, in your case, you want to optimize different things for different people, right? I mean, a person with arthritis, you'd want them not to have more than 90-degree angles.
Right.
But like an elderly person in a wheelchair, you'd want them to have proper access to infrastructure.
Right.
So have you thought about that? How you could adapt what Dijkstra's and A-star do, which is find the shortest path, into something that finds a shortest path with side constraints?
Yeah, haven't thought that much about it, but I do know Dijkstra's algorithm. Even though A-star is more faster, Dijkstra is more, I want to say more accurate from what I've looked up. You know, A-star, like I said, is more faster, so I'll probably think about using Dijkstra's for people, like I said, the wheelchair and the elderly people, whereas A-star would be mostly used for fastest route.
So you are onto something here, right? Dijkstra's is an exact algorithm, A-star is a heuristic algorithm.
Yeah.
So fundamentally, you are right. Like one of them is the exact, the other one is the faster version of the two. But I think that you would have to consider how you're going to incorporate all these different details. So you're not only looking at the shortest path, or like as far as distance, you're not only looking at the number of traffic lights, you're not even only looking at the traffic signals, right? You're not only looking at the speed signs, your speed limits. You are looking at a combination of all. So I think that you're going to have to, like on Monday, you're going to have to start thinking, how do I combine those to use the tools you have?
Okay.
Okay?
That makes sense.
Alrighty, good afternoon, everybody.
Good afternoon.
My name is Emmanuel Terrell, and I am under the mentorship and advisement of Dr. Ariel and Dr. Draw. And today I'm talking to y'all about hydrologic modeling of a small agriculture catchment is the word I'm looking for. So, just raise your hands. How many actually been on the farm, actually worked on the farm? Just a quite few. So, as we all know, just like humans, our farms need water to grow. And just to keep vegetables, just like some of our other fellows here, that they work on food banks, we can also use those foods, the crops that we grew, for those food banks. And so, today, I'm the outline just like everybody else. And talk about, of course, agriculture, which I just went over. And what is a catchment? A catchment is just a medium size of a watershed, of a basin. A watershed is just smaller. It's basically like a pond, or basically just like a pond. And basically, all these go by size. So watershed is the smallest, then a catchment, and then a basin, yes, all by size. And hydrology. Yeah, this is the definition I got from Webster Dictionary. Basically, a general definition of hydrology is basically how water moves while it comes from precipitation down to the ground, how it moves while going through that process. In North Carolina in North Carolina, we also known for a drought back in around 2002, where at that time we had to limit our time using water by people couldn't water the grass like they wanted to, couldn't water the plants, wash the cars like they wanted to. As that time goes on, we've gotten better at it, and to stop these droughts going on, I have picked up some help tips say about that, tends to help go on through help the situation. One, we're using the water that you don't use. When you drink a bottle of water, drink half a glass of water, 9 out of 10 we just pour it back down the sink. Also, we could also just easily just pour in one of the plants outside or outside, or just you see around the house. Use a shower bucket. With the raising hands, how many people wait till the shower gets real hot and you see just let the water just run? Okay. Sorry. Well, at that time, while the water just running, that's a lot of water wasted. So at that time, how about you put probably like a 5-gallon bucket in the shower and see how much that is used. After that water is used, you can use that for either washing crop, well not washing crop, like the crops you picked up, just wash that, or warm it up and just use it. You guys use that for cooking sometimes. Just save on water. The pasta water. At first when I read this, I thought that was crazy. But when you use the pasta water, you also save that and also put that in your plants as always. With everything else I've been talking about. A plastic tub of water when you wash dishes, basically some people, I do. Sometimes I use my dishwasher, but when I'm forced to not use that, I've used basically let the water run and let it keep going as when I'm done. When you use a tub of water, you just have that tub, go out and just basically have that set tub. We just wash and you don't have to use no more running water. Just use that water that you have. Let's see. The sweep don't spray. People usually, I know my uncle, he uses power hose and spray down his driveway. That's also wasting water. It'd be better off just using a broom and just dry sweeping it. And the rain barrels. You get a barrel, put can't remember the word right now, but the little extractions from like coolers and whatnot, use those and put up under your gutter. Those are also forms of way you can save on water for the universe and for the world. My research goal is basically making a model of an agricultural catchment using Apex model. And my plan is to use the one here at A&T. I'll select the catchment which I set up here at A&T, select the model which would be XPEX, develop it, and use the model to develop a solution. I keep papers that I'm getting from my mentor and my advisors. This first one basically kind of helps understand what Apex model is. And that really did help me with because that when I first got it, I did not know what it is at all. So this paper right here kind of helped me with the terms that I use at Apex and what it is. And right here, this is a paper that was used when they did something like this back in in Texas, where they used Apex model and basically can't find what I'm looking for, but when they used it, they helped develop it. My methods and approach to this, the data I am planning to collect is the topographic, which is the digital elevation model. Then the weather, basically just look at the forecast and see what we're gonna use for the future. Like, so tomorrow it might be raining, so I can plan ahead and see what I'm used for. The land space and cover, basically just where I'm going to use it at. And so what type of soil and what kind, like, let's say if there's been like an oil spill and happened in the grass, the oil digs down. So you gotta make sure that the oil is clean and good for growing. And as time goes on, if I have enough time, the land management is These are, okay, let me start. My main focus is not on the land management as of right now. But as time goes on and as I need it, I will go through these steps. I'm using catchment and GIS. And the tools I say is how to get water, how to recycle the water recycled, put it into the catchment and use it for put back in the fields in the form of A&T. Apex model. Apex model is basically I use it to basically just model what I'm looking for. Just the catchment. That's basically, I apologize for my words, but I'm really just looking for the catchment, just the model of it. And GIS, the geographic for information system, excuse me. And that, after that, I can put in the data that I collected, like the soil, the weather, and how much I can predict. Use that into GIS and hopefully get a, I won't say precise, but accurate model. Any questions?
So, I mean, is there a specific, or is it A&T's form that you're
Yes,
trying to model? Is that right?
Yes, sir.
And do you have a basis? I mean, do you have information that lets you compare what you might observe to the model that you have here? Compare that actual behavior at the farm itself, or?
My plan is to actually have permission from Dr. Ariel and Dr. John to actually go see it myself. If I get a visual scene for it, if I look at it for myself, that's my plan. Does that answer your question?
No.
Okay.
So, what is it that your model's going to do? Okay, you're going to put in information to it. What is it going to?
The whole plan of this is the water that we recycle, how we put it into the catchment, and in the catchment, how we get back into the field. Just like if you pump the well pump from the groundwater, and that runs dry, wells you get the water from. And so we're trying to make sure that the groundwater will never go dry. That's the whole plan.
So let me answer a little bit, because many of the talks that he used in those presentations he saw for the first time. So he's not that clear, so because it's first couple of weeks. So what he's trying to do is he's trying to put elevation, he's trying to put long-term climate data like rainfall, temperature, and he's trying to put soil, what kind of soil is there, how deep is the soil, and what is the elevation, slope, everything into the model. So once he puts that, what he gets it is how much water flows along the landscape and how much collected in the pond, in the reservoir, that is in the agriculture, that is in the AIT farm. So that water he is going to model in different scenarios in dry conditions, how much water can be stored in the pond. And the reason he wants to know the water amount is, quantity is, that water can be recycled back into the plant. So when there is a drought, if we have enough water available on the pond, we can put it back and use in those crops. So the main reason he wants to do this modeling is to find the water availability in that pond.
Thank you, Dr. Ariel. Any other questions? Yes, ma'am.
Are you going to simulate it, or you want to actually do it?
As of right now, I cannot get the software onto the computer, but as soon as I get it, I am trying to do it myself. All right, thank you.
This is the last presentation, we'll get started right away. So finish it early. I just want to remind you guys, after we finish here, we'll be in faculty lounge. The schedule is for some donuts and so on, right?
Open up another college score.
Really?
Go to accessible.
Original claims.
Good afternoon, my name is Neil Tuller. My project is Kinetics as Biometrics for Security. My mentor is Dr. McCullough, and I'm also working with a grad student in Cleveland. So, biometrics has been more reliable and efficient for identity verification. Some examples of biometrics are face recognition, fingerprints, and retinal scans. So, poor surveillance is an obstacle that can affect the identification process. Passwords and ID badges are proven not to be secure enough for human identification. It is becoming easier for these things to be replicated. Therefore, there's a need for new security measures. Gait kinematics is being researched as a new form of biometrics, and gait is the progression of humans through the movement of lower limbs. My research problem statement: gait has not been included in biometrics as a security measure, and this is due to the lack of accuracy in algorithms identifying people with clothing or accessories such as like baggage and things of that nature. My research goals include, first I have to find which algorithms I'm going to use. We haven't really decided on a set of algorithms for modeling gait. Then I will program those algorithms for identification into MATLAB. After that, I will test the algorithms using existing gait data from a database. We also haven't decided on which gait database we're going to use, but the grad student that I'm working with is working on that right now. My key papers. My first key paper is human group activity recognition based on modeling moving regions, insert dependencies by Kyle Stevens. In all my key papers, the thing that they have in common, it provides a set of algorithms in order for identifying moving objects like in a video or a video sequence. So in this first key paper, it gives a technique for transforming visualization into numerics. It's a method for observing human activities and then using those activities to identify humans. The first step is the optical flow, which is estimated from video sequences. It gives two different approaches. And in the first approach, the optical flow is depicted into histograms using the Gaussian mixture models with the specific activities as the mixture components. And the Gaussian mixture model allows the observation of a subpopulation within a population without identifying that subpopulation by a specific data set. In the second approach, A histogram is computed for each section of optical flow containing an interconnected region of movement using the expectation maximization algorithm. This algorithm is shortened EM. The EM algorithm is basically an algorithm for finding the maximum likelihood. It has two steps. The first step is the E step, and it creates a function for the expectation of the log likelihoods. And then the M step computes the parameters maximizing those likelihoods. In the second approach, once the training step is complete, the appearance of new activity is detected and seen by observing the statistical consistency. We do that with another algorithm called the Kullback-Leibler divergence. Short is KL divergence. And in the KL divergence, it gives the expectation of the logarithmic difference between the probabilities of two activities. So it's gonna use the probability to basically discern if the activity is the same or different. The next key paper, Walking Gestures Recognition Based on a Novel Symbolic Representation by Zin Yao. Basically, it gives a way to represent time series and identify movement objects in a video. It uses a set of algorithms, about 4 different steps. And then in the first step is you use piecewise aggregate approximation, so in PAA. And with PAA, it's a linear representation method that transforms high dimension data into low dimension. It improves the efficiency of finding matching patterns in a large database containing time series. The PAA separates the time sequences into equal length segments. Then the value of each segment is approximated using the mean value of all the data points in that region. The next algorithm is the symbolic representation. That's the next step. The symbolic representation separates the new time series with the number of breakpoints defined by the Gaussian distribution. In the last step, in the last 2 steps, you build a distance table and then you calculate it. So the distance between the symbols are computed based on the average values of each segment, and then the output will be a distance table that characterizes the distance between any 2 videos. And my last key paper, Gate-Based Authentication Using Gate Information Image Features by PR. It gives a new period-dependent gate representation technique based on information set theory. It finds the gate information image is computed using information set-based features based on the Handman anaerobic entropy function equipped with free parameters. The extension of the expanded entropy function is a modification of Shannon's logarithmic entropy function. It finds the uncertainty of the pixel intensities in a silhouette image of a person over a gate cycle. Then the polynomial gain function of the Handman anaerobic exponential entropy function provides the flexibility to adapt its parameters to deal with the uncertainties. So it proposes 2 new features. And the different algorithms will be GIIEF, which is gate information image with an energy feature, and then gate information image with the sigmoid feature. The features are then tested using the nearest neighbor classifier with Euclidean distance measures. In the methodology of my research, I will be modeling gate kinematics from an existing database. Then I will be choosing developed algorithms to test the data. Some of the algorithms I looked at were from my key papers: the KL divergence, the piecewise aggregate approximation, and the Handman anaerobic entropy function. We haven't decided which algorithms or set of algorithms we're going to use as yet. The computational models, well, I'll just be choosing an algorithm to use to model. And then I'll be modeling the data in MATLAB. The results that I seek to get will be the detection of the consistency between the data and the model, making accurate identifications. So basically, I want to make sure that the model can correctly identify a person based on that data. This just explains, just shows the different kind of algorithms I'll be using. So like the KL divergence, basically it has a mean vector and a diagonal covariance matrix that we will be taking the log of basically. And then in the piecewise aggregate approximations, it's just different steps. So the original time series is converted to a low dimension image, making the dimension of the new database 1/90th times of the dimension of the original data set. Then the new time series is separated by a number of identifying breaking points based on the Gaussian distribution. The distance between the different symbols are computed based on the average values of each segment given the number of breaking points. And then the distance table is created and used to characterize the distance between any two videos. The distance between the videos are then computed according to the sum of the distance of all the corresponding symbols. These pictures are just the steps that I would probably put into MATLAB to compute all of that. In the last algorithm, the Hammond-Anderson entropy function, the energy feature is the result of finding the uncertainty in the information values, which is H sub ij, using the original agent mu sub ij. And then for the sigmoid function, the information value I sub ij and mu sub ij is incorporated into the sigmoid function, which is a logistic function that represents the S-curve. And these are my references.
Now, the data set, have you seen the data set? Is it images?
I'm not sure. I think it's gonna be basically like the video sequences. They're probably gonna be using video sequences. I'm not sure. Like I said, they haven't selected a database with the gate kinematics.
So when you said go back to your slide that says the goal, right? Of you want to compare the data with your model. The last goal. So how do you foresee doing this? There'll be like one video that will be the standard.
Yeah. So
then
you have a video that you basically like record, and you save that, and then you basically compare, I guess, a new video to that standard video and see if it can detect a difference in the scenes of the video. So we'll probably have like a video just showing people just walking, and then another video just having a little alternation of how they walk, and then we're gonna test to see if it can identify those differences.
And it could also be for different people.
I'm assuming so because the gate data will be a variety of people.
Just, I would, this is, I think what Dr. Ram was kind of getting said, I would assume that kind of the core reason for this is to be able to
use gate
watch somebody
kinematics
walking by and identify what person that is.
Yes. So basically, like, say we have a camera over a door, and then we want to see if they say, okay, probably they check in as this person, and then they walk through that door. If their movement matches the movement in the data in their system, as that person. So probably to use gate kinematics, they're probably gonna have to store a bunch of people's movements, and like say for a company, everybody probably has to walk a certain way through a door, and then they're gonna record it probably during their orientation, and then as they're checking in, when they go to work, in order to confirm that it's them, they're gonna have to walk that same way through the door.
I will say the image analysis and dynamics of program is not going to be trivial. So to have three methods could be a big task. So you're assuming you have, for every subject, you have a kind of a baseline video that you can use for comparison to.
Yeah. Yes.
Do you know how sensitive the algorithms would be able to tell? Just say, for instance, somebody stubs their toe, they may not be walking the same way. Would it be sensitive enough to be able to tell a difference between the way a person walks with or without like a stub toe or something?
So that's basically what we're working on. So like in addition to like clothing and accessories, like if somebody had a deformity after the fact, like after they're recording, like will they still be able to tell if that's them?
Any question? Very good, thank you. Thanks everybody for evaluating. Don't mind if you come to faculty lounge, you can do that for another half hour. Just all the stress. Okay, so let's go to the faculty lounge. I just have to go upstairs. Get those forms, kindly drop them off in the back. I should have, I'm hoping I have 4 sheets for each of you, from each of you.
All right, okay. Yes, sir. He kind of summarized it, right? You said like 12 minutes. He said like 8 minutes. So it's basically just like if anybody forgot what you said at any point, he just kind of summarized it. Like I thought your project was more focused on how can we save water, and he was saying like what you're going to do with it.
You get it to the base, so it's essential.
What did you think? Which one did you like? They were good then.
Yeah. So my first slide?
Yeah.
I won't be joining you at the social. I'm still. I had a cold last week and I'm still not at 100%, so I'm trying to avoid as many social.
Thanks.
Okay, just pretend you are saying something.
Okay, hold on, let me have my clicker. This is my first time using it.
That's good. Thank you.
Welcome. Oh, let me get that off.
Go upstairs and agree with this stuff. No, right? I'll go this back. You can deal with